I will begin. Dear Father, we thank you for this day. Pray that you'd help us use this time wisely, just to just wrap up any questions I have about the homework, and just help the students to enjoy the break. In your name we pray, Lord Jesus. Amen. Okay, so this were your daily quiz questions for today. I'll start with problem 1. So the question was to calculate the integral of x squared dA over the purple hatched region. All right. So one of Emily's ideas was she could calculate the integral over the whole circle, right? And then just subtract the integral over this region times 2, I think, right, by symmetry. Yep. And I think that's legitimate because x squared is the same above and below. So it stands to reason that if we doubled that integral and subtracted that from the integral over the whole circle, that's one way we could calculate the requested integral. But I encourage you to go a different direction, so that's what we have here. So when we're thinking about the integration region, right, we have to think about rays that come from the origin out to figure out what the inside radius and the outside radius is. And there's two different stories. To the left of the y-axis, you see when x is negative, we have the inner radius is 0, right? But the outer radius is 1. And so that's why I say from pi over 2, which is up here, to 3 pi over 2, which is down here. From pi over 2 to 3 pi over 2, we have 0 less than r less than 1. That I need to integrate over this whole piece like that, right? But on the other hand, if we're where x is positive and we take, a ray out from the origin, then you can see that in this part here, we have an inside radius which is possibly non-zero. And I've described the purple region with this set of inequalities up here. Minus pi over 2 less than theta less than pi over 2. In that, we have 2 cosine theta less than r less than 1. Now, the 2 cosine theta Emily figured out. I originally stated the circle here as x minus 1 squared plus y squared equal to 1 after I was kindly encouraged to make the problem easier, and I listened to the request. So, well, anyway, it's not important. So how did she know that this is r equals 2 cosine theta? Well, here's the work over here. So we have x minus 1 squared plus y squared equal to 1. So she's like, okay, so that's x squared minus 2x plus 1 plus y squared equal to 1, right? Which is actually x squared plus y squared equal to 2x. Then converted into polar coordinates, that's r squared equals to 2r cosine theta. Divided the r's, haha. R equals 2 cosine theta is actually that circle. Now, if you still have a more working knowledge of calculus, if you've just taken calculus 2 and you just got done studying for your final, you might not need to do all this. You might actually kind of just know that's r equals 2 cosine theta, right? If I just got done teaching calculus 2, I probably would know that. But you guys, who knows when you took calculus 2, and if calculus 2 even covered polar coordinates in the way I'm talking about, so whatever. Here's how you do it. Now, so the lower bound is 2 cosine theta. The upper bound is still 1, because it's still the unit circle that's the outer edge, right? And so the integral has to get broken up into 2 pieces. X squared dA, we integrate from pi over 2 to 3 pi over 2, integrate from 0 to 1. That would be the red part. And then what's this r cosine squared theta? That's x squared, right? This is the x squared. And what's this piece right here? This is my dA, right? Which is r d r d theta. And then then plus minus pi over 2 to pi over 2 from 2 cosine theta to 1 of r squared cosine squared theta r dr d theta. Yeah. Now, I guess I could be foolish and try to do these. Nah. It's actually probably useful for you guys to see me suffer through that a little bit. Let me try. So we're integrating from 0 to 1 and the top integral, right? What do you got here? R cubed integrated from 0 to 1 gives us what? 1/4, right? So we actually have got 1/4 the integral from pi over 2 to 3 pi over 2 of cosine squared theta d theta. That's what the first thing simplifies down to. Cosine squared theta d theta from pi over 2 to 3 pi over 2. What's that look like? I mean, what is, let's see, how far is that? That's what? That's pi, right? that's half a cycle. So if you think about, what's the integral of cosine squared over a, what's the integral of cosine squared over a whole cycle? What's the integral of cosine squared plus sine squared over a whole cycle? It's 2 pi. But cosine and sine are symmetric about a whole cycle. So that means that the integral of cosine squared from 0 to 2 pi is pi. Which means that since this is the integral of cosine squared over a half a cycle, this is pi over 2. All right. Anyway, that's not going to free me from the terror, which is this integral. I mean, we're going to have to face the music here. I can't avoid it. Again, the r cubed integrates to r to the 4th over 4, right? Evaluated from 2 cosine theta to 1. So when I actually do that, what do I get? I've got myself a cosine squared theta times what? Divided by 4, let's say. And, oh, yee. Well, the 1 is fine. 1 minus, what do we get? 1 over 2 cosine theta to the 4th power, right? Let's see here. So that gives me pi over 8 plus, let's see here. So I've got 1/4 the integral of cosine squared theta. Yeah, what did I do?
Why is it 1 over 2 cosine theta to the 4th?
That's a good question. That's a really good question. I wish it was that, though. Because if it was that, it would be ever so much more nice than what I'm about to write. Oh, no. Oh, it's so much worse than, I mean, that's just secant. Secants are nice. Secant to a 4th power, it's not too bad. But this is not that. You're right. Thank you, guys. 2 cosine theta. Why did you have to correct that mistake? Yeah. Yeah. Plus 16 cosine to the 6th theta. D theta. From minus pi over 2 to pi over 2. Great. So the cosine squared thing integrates to pi over 2. Because again, if we integrate cosine squared over a half a cycle, we'll get pi over 2, provided it's a nicely situated half cycle, which that is. The cosine of the 6th, though, that's just nasty. Do you guys know how to do that one? Nah. Really? You should have learned it in calculus too.
Can't we separate it into a few?
You could go to the recursion formula, or if you just wish to face it in direct battle, here's how it goes. Oh, you could use Wallace formula, which I never remember. Yeah, that's true. So this is really cosine squared theta, cosine squared theta, cosine squared theta, which is 1/2 squared times 1 plus cosine 2 theta cubed, yeah? Which is 1/8 of 1 plus 3 cosine theta, cosine 2 theta, plus 3 cosine squared of 2 theta, plus cosine cubed of 2 theta. Is that right? What's that? That should really be a 3. Yeah. So, yeah. And then, of course, this right here, of course, is 3/2 of 1 plus the cosine of 4 theta. And then the cosine cubed we can integrate in a way similar to the way we integrated sine cubed yesterday. Anyway, you are free. If you for some reason come to face an integral like this in your homework, you're welcome to use Wolfram Alpha or something. All right. I mean, this was if we were in the heart of darkness in calculus 2, I might actually want you to do it, but here it's kind of not the point. Yeah. All right, enough about that. The other problem. So what I'm trying to say is that this is a pain, and I really shouldn't have even started it. But I love integration too much, and I will just start doing it if I'm not stopped. So
You don't love it that much.
yeah.
You don't love it cosine.
Well, the thing is, while I love integration, I also have other responsibilities, which is to try to at least let you guys ask questions about homework today. We're running out of today. I'm not careful. So the other problem, but this is, I mean, these are both helpful for your homework, right? This one, problem 2, I start with this integral over this rectangle, or maybe it's a parallelogram, I'm not sure. It's probably, I don't know. Anyway, so you got this quadrilateral, at least. Here's I gave you the corner points, right? And I said calculate this integral. I even was so nice as to suggest that we make a u equals 3x minus y substitution and a v equals to x plus 2y substitution. The reason to do that is because then the integrand becomes nice, v and square root of u. Oh, thank you for the square root, Emily. I see you fixed my, that's good. And so when we're doing this integral change of variables theorem says we had to change the bounds. There's the integrand changed, and I'll talk about the Jacobian works out to 7 for reasons that are explained over. Let's talk about the Jacobian first. The Jacobian, partial x, y, partial u, v, is kind of a pain to calculate directly here because we don't have x and y as functions of u and v, right? So we use this trick. It's reciprocal of the inverse Jacobian. The inverse Jacobian we can calculate, that's ux, vx, uy, vy, which you can calculate directly from here. 3 minus 1, 1, 2. The determinant of that is 7, so that's why we put a 7 there. Uh-oh. Uh-oh. I have failed to, it's my fault. I lost a very important thing here. Sorry, I made it ugly, but it's just 1/7. So now let's see here. Now suppose you didn't know this trick to find the inverse. To find the Jacobian in terms of the inverse of the reciprocal of the inverse Jacobian. Well, you could also solve for x and y using some matrix algebra if you like, or just regular. I mean, this is how I do it. If I'm going to solve this system of two equations and two unknowns for x, y, I write it as a matrix. This uv times that matrix equals xy. I multiply by the inverse matrix, and that gives me that xy is equal to 1/7 2u plus v, 1/7 minus u plus 3v. And so once you have this formula, x equals to this, y equals to this, it's easy enough to see that the Jacobian, right, is what? So what's the partial derivative of x with respect to u? It's 2/7, right? Y with respect to u, minus 1/7. V with respect to u, 1/7. Y with respect to v, 3/7, right? So that gives us 6/7 plus 1/7, which is 1/7 by direct calculation. So either by direct calculation after you do algebra, or by the reciprocal trick, you can calculate that the Jacobian factor here is 1/7. All right? Now, then the other thing is we need this nice result, which is again from linear algebra actually. If you have a linear substitution, that moves lines to lines. So if you're given a linear region, and you have a linear substitution you're making, you just have to figure out where the corner points transform to, and that will tell you what the new transformed region is. So here, if we plug in x equal to 0, y equals to 0, what happens? We get 0, 0. So this a moves to a prime. When we look at 2/7 minus 1/7, I called that b, then we get b prime is 1, 0, so that's the b prime is 1, 0. This point maps to that point maps to this point, so in the new variables, in the uv plane, our transformed region is just the handy-dandy unit square, which we much prefer to do the integral. I mean, if you did the integral in x, y coordinates, it'd be a pain, right? You'd have to break it up into like a type 2, two type 2s or two type 1s. It'd be a mess. But over here, it's not too bad. So we just have to integrate from 0 to 1 in u and v. Here's our transformed integrand. Again, the Jacobian factor. And this is, of course, all by the change of variables theorem. And there you go. I think we get 1/21. So, well, that's it for the daily quiz stuff. Do you guys have questions about the homework? I'll put it up on the projector here so we can look at it together, and I'll try to tell you useful things. So what's the next test on? Just looking ahead next week, right? What?
Can we have dot products on the next one? Nothing we were seeing.
Amazing. I mean, seriously, it's 11 minutes to the end of class, and no one has said anything. It's amazing. I can't believe I got away with it.
Said that you had passed it around earlier.
Oh, so I just should do that every time. But then I'll actually forget. Yeah. Are you guys doing anything exciting over the break? It's just an extra. You say it's just an extra day. Well, that's what you say. But I was talking to somebody I work with in Awana, and I know she said she's going back to her family or something on next Friday. So she was debating whether or not she was going to come to the Tuesday, Wednesday, and Thursday class. I mean, she's missing Monday. She's already got family obligations for Friday, so why come to the middle of the week, right? You're engineering and math majors. It doesn't make sense to you, I know, but I mean, how would that work for you in calculus? I think I'm just gonna take a week off, see how it goes, Yeah, yeah, badly. Yes.
Problem 88.
Yeah, this one is literally the one that I just covered up. I mean, so you make a x equals 2u, y minus 2x equals v substitution, and it's pretty much problem 2.
Okay.
Yep, just same idea as problem 2. 90?
Yes, please.
Oh. Okay, so this we need, okay, so how did we calculate the volume of a sphere?
Isn't it 4/3 pi r cubed?
4/3 pi r cubed, that's right. And how did we actually calculate it? The way we actually calculated it was to change to spherical coordinates and to integrate rho squared sine phi d rho d phi d theta, right? So to be successful here, what we need is the analog of spherical coordinates for 4 dimensions. So in 4 dimensions, so here's hyperspherical coordinates. First of all, we will let, well, I guess we just let rho equal the what? the square root of x squared plus y squared plus z squared plus, you guessed it, w squared. Or is it t? Oh, I use t. Space-time, t squared. So there you go, the 4-dimensional radius, like that. And then what you do is you put x is equal to rho cosine theta sine phi. Y is equal to rho sine theta sine phi. Z is equal to rho cosine phi. You're like, well, that's just spherical coordinates. That is true. Up to this point, I've just written for you spherical coordinates. Here's how you make hyperspherical coordinates. You guys know what happens. What happens if you if you sum the squares of these, x squared plus y squared plus z squared, what do you get? You get rho squared, right? But we don't want that. We want x squared plus y squared plus z squared plus t squared, right? So I'm going to have to put a rho. It's going to have a rho, t rather. And so what you do is you just add another angle. Say cosine of beta. And then all I do is I slap a sine beta on these guys. With this system of coordinates, if you have x squared plus y squared plus z squared, you know what you get? For all the usual calculational reasons, you get sine squared, rho squared, sine squared beta. So when you add this to t squared, you get rho squared cosine squared beta plus sine squared beta, which works out to what you want. So there you go. These are the coordinates. So all you got to calculate
Yeah.
Oh.
Is there an equation for a 4x4?
Sure.
Is it?
Yes.
Great.
The answer is it's not that more difficult.
More than that,
Great.
It's not that much harder than a 3x3. You just have to do it multiple times.
Great.
I'll tell you this much. It's got a rho cubed in it.
You don't have it memorized?
No. I mean, this, of course, what that means, I'm going to have to erase my motivational. This doesn't really help you anything. I mean, this is, that equation I just erased doesn't really help you with your problem. These are, in these coordinates, the sphere, the hypersphere, this thing, the bounds is that 1, so it's unit hypersphere. You got 0 less than or equal to rho, less than or equal to 1. Theta still going between 0 and 2 pi. But both the phi, you see that both the phi and the beta, they both appear in the same way. They're both ranging from 0 to pi. Okay? There's only one theta. But you kind of have added another sort of, like an additional phi in some sense. This, yeah, it's a 4x4 determinant. So you've got x rho, y rho, z rho, t rho, x theta, y theta, z theta, t theta. Do I have to write it all out? I guess I'm this far in. X phi, y phi, z phi. You're like, what are you complaining about? You don't have to calculate it. Well, you don't have to either. I mean, if you want to get credit for the problem, I guess you need to. But x beta, y beta, z beta. I mean, that's why these points are not easy to get. This particular problem. Calculating this is a pain. Now, you were asking me actually how to calculate the determinant of a 4x4 matrix. Was that really your question?
Yes.
So,
Is there a formula for it?
yeah, there is. So the determinant of A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P is equal to A times the determinant of F, G, H, J, K, L, N, O, P minus B times the determinant of E, G, H. There are none. I, K, L, N, O, P plus C times the determinant of E, F, H, I, J, L, M, N, P minus D times the determinant of E, F, G, I, J, K, N, O, P. Oh, M, N, O.
Debating taking that note at that time.
I mean, you could do this in Mathematica or something if you wanted to. That'd be cool.
Or you could just look in the notes. You get the answer in the notes.
Don't tell them to look in the notes.
But we have to sign a statement saying we read the Jacobian. Make us look in the notes.
Oh, I cleverly hid the answer in the notes. Yeah.
Sorry?
I cleverly hid the answer from you in my own notes.
You didn't even show it in the notes. You just assumed the answer.
Oh, that's true. So I actually want you to work it out is the point, yeah. At least you know what you're working for. I mean, you know what you're working towards, yeah? Or not. I mean, I don't know. It's up to you guys. Where was that thing? Did I have it over? So guys, before I got distracted by, well, you, mostly, the next test is on multivariate integration. That is true, but what else is it on? Optimization, right? Yes, we still have not been tested on Lagrange multipliers and the second derivative test stuff, critical points, right? So that's part of this test. What am I searching for? I'm searching for hypersphere, I guess, right? So here's what Nathaniel was, and who else was talking about it? Ripken? Yeah. So there it is. It actually works out to pi squared r to the fourth divided by 2. So really, the only thing that's left for you to do in your homework problem is to actually work out this monstrosity. Yeah. So if you don't, I'd probably still give you half credit. So it's just up to you. I mean, it's a question of, what's that?
Work out the determinant is all we got left to do.
Well, and understand that. Yeah. But I think understanding this is like a lot easier than doing that actually for these. I mean, these are awful, right? It's quite horrible. Well, is it a lot of zeros? I guess the T row, we got zeros here and here, so probably expanding on the bottom row is the smart thing to do. But I didn't tell you how to do that. Sorry. But you, I think. Well, anyway. There's actually another way to calculate this in terms of what's called the wedge product. Have I talked to you guys about that at all this semester? All right. Well, all in good time.
Is the test basically on chapters 5 and 6?
The test will focus on the homework which has been due since the last test. So mission 5 and 6. Yeah. Yeah.
Isn't the input going to be like the same as last time or the first time we took it? I mean,
The what?
The math battle.
Oh, math battle will be more like the last time. It'll be, teams, and it's a Tuesday, better than a. So you guys have a little bit longer, so it's a Tuesday, but it should be a mix of integration and an optimization. Probably less problems because these problems take longer, right? So, yeah. Well, thanks guys. Have a good break.